The second presentation is by Rachit Bhatia,
Yes.
and his presentation will be on initial orbit determination of GEO resident space objects from Earth Moon L1 orbit. Right, the floor is yours.
Hi, I'm Rachit, and I'm going to present on the project that I did on initial orbit determination for GEO RSOs in, from Earth Moon L1 hello orbit using Optical Observatory. So, for a brief introduction to orbital debris is classified as any man-made object in orbit around the Earth which no longer serve any useful purpose, and they can be generated by any of these and classified in various sizes. And we're gonna be looking at the smaller the size, the harder it is to observe. And so why do we want to talk about orbital debris? It is basically because global space economy is exploding, and it is becoming more and more relevant to sustain our lifestyles. But at the same time, it is also being threatened by itself, and as the number of launches are increasing per year, they are heading towards what Kessler syndrome predicted in 1978, that as the number of as the number of objects will grow in orbit, the more we are heading towards catastrophic events, which will result in more orbital debris objects. So, what can we do to prevent this? So, debris mitigation, as defined by IADC, can be done by 3 steps: preventing, removing, and limiting. Removing is basically what we do with active debris removal, and that is what we saw on day 1, PPDs. But for preventing and limiting, that is what the best option we have for now based on technological constraints. To prevent and limit further growth in orbital debris, we require to first detect and track and identify the orbital debris that we want to remove. For this, we have basically 2 approaches as of now. One is optical or radar-based optical, and the second one is radar-based observatories for surveying and tracking these objects. But they come in both ground-based and space-based domain. But all of these approaches have their own constraints. Like optical might have less accuracy from the ground, and while radar is limited to LEO. So we propose to station an optical observatory in L1. L1 is basically a Lagrange point in Earth Moon system, and this will help us provide a better geometry so as to solve our problem in a better way. Lagrange points are the equilibrium points in a 3-body system, such that the distance of that point from the relative to other 2 bodies stays constant, and that is why this will help us to get a better view of the objects around Earth. According to a paper that I cited, from this point, from L1 point, about 48% of Earth can be observed at any point of time. To verify what we are proposing, we need to follow these objectives. We need to compute observability of GEO RSOs from space-based observatory. We need to compare that with the existing approach to know whether it is a viable solution or not, whether it is worth putting an observatory over at the L1. Then to finally analyze the feasibility of the proposed mission and check if the conjunction of the 2, the existing approach and the proposed approach, will be a better solution. So what is the method that can be applied? So here we have considered that we have a perfect knowledge of an L1 hello orbit and the GEO orbit. We have considered GEO object as Intelsat 29E. It is an ESA satellite which is in near circular orbit with 0.1 degree inclination. we have chosen this because it is an easy target to start computing our preliminary results. I want to define halo orbit. Halo orbit was coined by Robert William Fokker in 1968, and there are around 6 types of halo orbits. Here we have used one of the type, and we have assumed that we have perfect knowledge of the satellite in this halo orbit, and this can be seen over here. And the GEO satellite orbit has been plotted here, and this is in CRTPP frame. What is CRTPP? CRTPP is defined as circular restricted 3-body problem. A general 3-body problem has 10 constants of motion. 3 linear constants of motion, 6 linear constants of motion, 3 angular constants of motion, and 1 energy constant. 1 constant of motion from conservation of energy. But that doesn't provide us the best solution, an optimum solution. So what we do, we put justifiable constraints on our problem. As the term suggests, circular means circular orbits, and restricted means that the third body, our spacecraft, is very low in mass compared to the other 2 main bodies, that is Earth and Moon. So what we did, we generated L1 halo orbit and GEO orbit in CRTPP frame, and then we used batch processor to converge to an optimum solution about the orbit determination of our GEO satellite. In this, we used 1,000 measurements, and we propagated over 1 sidereal month, which is 27.3 Earth days. There is a time taken by Moon to go about the Earth. In this, we generated measurements by adding noise of 1 sigma error of 2 arc seconds. Here is the result that I've got. This is the result I've got from space-based observatory. This is the covariance matrix. And this is from ground-based observatory. As we can see, the variance on the diagonals is pretty small for space-based observatory. And similarly, for ground-based observatory, it is further smaller. This can be explained by the fact that the distance between the satellite, the target object, and our observatory in L1 is greater than that between the ground observatory and the target. Further, the correlations are nearly equal. These are the correlation on the upper triangle, and these are the correlation for the space-based observatory, and this is for the ground-based observatory, and they are nearly equal, but it is somewhat on the higher side for the ground-based observatory. Based on these analyses, I can conclude that as per our preliminary results, L1 halo orbit can provide a better geometry to look into to observe space debris in GEO orbit, and also it provides a better it helps us better to catalog GRSOs. Further, I added this slide as a backup slide because I got these results right at the last minute, and this is the visibility that I've computed from L1 halo orbit, and this might not be visible. This is for 0.2 meter object. If a GRSO is 0.2 meter in radius, if it is 2 meter for the blue line, and for the black line if it is 12 meter. And this is the formula that I've used. Thanks. Any questions?
Any questions?
Yes. You said the halo orbit was a better orbit compared to
the ground-based observatory.
Ground-based. Okay.
I haven't compared any of the other space-based observatories, but I've studied for them, and they are basically in sun-synchronous orbit around Earth, and they can only look at a part of GEO orbit, not complete GEO orbit, as that can be observed from L1 orbit.
And was your observatory? It was in. You modeled the halo orbit, right?
Yes.
What if you just simply put it at L1 instead? Would the results change much? Do you think? Just putting the observatory right at L1.
We cannot. We have to put it in certain orbit in L1 so that we have periodic motion.
I have to.
Alright, let's thank our speaker.
It's really